Have you ever questioned the nature of reality? Ever pondered over the statement, appearance versus reality exists? When we sleep, it is difficult to tell the difference between reality and dreams. So, how can we navigate the blurred border between what is actually real and what is purely a figment of our imagination? In the scientific world, an object is considered real if its properties are established before observation. There is an old philosophical question about a tree in a forest. Is there a sound if it falls with no one to hear it? A quantum scientist would argue that sound existed, but you couldn't be certain the tree did. A pineapple, for example, can maintain its green color even when unnoticed. The quantum world, on the other hand, appears to follow its own set of rules. Recently, 3 brilliant minds won the Nobel Prize by demonstrating that our universe does not adhere to local reality. This revelation raises an intriguing question. If our universe isn't bound by conventional notions of reality, what exactly defines the place we live in? This question on the realness of the world will be the focus of the Nobel Prize. In 2022, John Clauser, Alan Aspect, and Anton Zeilinger were granted the Nobel Prize in Physics in recognition of their groundbreaking contributions to the discipline. The world is not as locally real as we would have believed, as their experiments with entangled photons and the violation of Bell inequalities crucially illustrated. We must comprehend the past to comprehend why this is such a revolutionary discovery. There was a period when quantum physics was thought to be philosophical and invented physics. If scientists were interested in pursuing it, they were either ridiculed or deterred, since they could not produce any real evidence that supported the notion. Before we delve into the major aspects of these facts, I think it is imperative to understand the concept of what realness is. That way, you get to understand better. So let's get to it. What is real? The definition of real has been debated by philosophers for decades now. However, physics now has a significant contribution to the debate. Local realism, a non-quantum mechanical definition of real, states that an object, such as a car, has definite properties independent of observational measurement, implying that the universe exists beyond our minds. Thus, in physics, real denotes that objects have certain properties, regardless of whether we measure them. In other words, the falling tree in the forest makes a sound, even if there's nobody there to hear it. And locality means that objects can only be influenced by their surroundings, and that this influence cannot travel faster than light. Our world must be real, because, as Isaac Newton believed, if you know the positions and velocities of all ingredients of our world, and identify the forces that influence them, physics can predict what the world would be at any time. In a simple experiment, fill the container with several radioactive atoms and wait. Normally it can be anticipated how many decay, but you can never know for sure which atoms will and won't survive, or fire several particles via a tightly spaced double slit. You can estimate what interference pattern will display on the screen behind the slit, but you won't know where every single particle will fall, even if they are fired one at a time. Some components of quantum physics appear to be utterly random, but are they truly random? What if we simply lack information? The beginning of the debate. The origin of this debate began in the 1930s, with the goal of Albert Einstein, Boris Podolsky and Nathan Rosen, EPR, demonstrating that the quantum world could provide results that went against our natural comprehension of local reality. In simple words, pairs of particles are transported in opposing directions to two observers in an EPR-type experiment, and detecting one of the particles instantly impacts the other, regardless of how far apart they are. Because it seems that the particles are connected or communicating faster than the speed of light, this phenomenon calls into question the viability of the local realism theory. As a result, a well-known EPR paradox, which holds that quantum physics only fully explains physical reality, was born. John Bell then developed these concepts further, formulating a theorem and devising experiments to explore this idea. Alice and Bob, two observers, measured the characteristics of entangled particles as part of the Bell test. Their experiments revealed correlations that local hidden variables were unable to explain. Stated differently, the behavior of these particles could not be explained by inherent characteristics or external factors. Rather, it validated the bizarre and counterintuitive consequences of quantum mechanics, according to which particles might be entangled and show instantaneous correlations, regardless of their distance. This marks the inception of the concept of quantum entanglement progression. What is the quantum entanglement? So what precisely is entanglement? Simply put, it occurs when a property in one quantum entity implies the value of the corresponding characteristic in another. To put it more simply, it's the connection between two particles' attributes. For instance, electrons have a characteristic known as spin. It's feasible to entangle two electrons such that their spin will measure as opposites. Thus, you can determine that the entangled electrons spin counterclockwise if you detect the spin of a single electron is clockwise. However, for the sake of both of our sanities, let's reserve that discussion for another occasion. Electron spin is not the same as, say, the spin of a basketball. It's based on angular momentum. Even so, the existence of particle entanglement can only be determined through measurement. A new theory of reality. Albert Einstein and other physicists suggested that hidden variables might exist and explain these quantum events without going against local realism. Particles that hold attributes that are not immediately observable would be considered hidden variables. The purpose of the Nobel Prize-winning experiment was to determine if these hidden factors exist. The work of John Bell in the 1960s laid the groundwork for experiments challenging local realism, the idea that particles carry predetermined properties independent of observation. Alan Aspect's experiments, inspired by Bell's theorem, confirmed the violation of local realism, indicating that quantum particles indeed exhibit behaviors that cannot be explained within a locally real framework. Thus, the Nobel Prize-winning experiments projected that hidden variables do not exist. This means that, as per quantum mechanics, particles do not have definite properties before they are measured, and their behavior can seem to be influenced non-locally, even over vast distances. Thus, if hidden variables do not exist, then particles do not have definite properties, and if particles do not have definite properties, then the universe does not exist. These experiments have raised significant questions about the nature of the universe, especially at the quantum level, where the behavior of particles challenges our classical understanding of local realism. The successful experiment. Physicists wanted to develop a means to complete an experiment. Measurement John Clauser's CH-SH inequality is one of the first and most elegant extensions of Bell's theorem work, which is now well documented. We are discussing the Nobel Prize winner here. Michael Horn, Abner Shimini, and Richard Holt's work renders Bell's theorem experimentally testable. The scenario they describe is similar to what we've discussed before. Two entangled photons are sent in opposite directions. Two observers, Alice and Bob, both get a polarizer to play within their setup, which lets them determine which polarization the light is in. Finally, Alice and/or Bob are randomly assigned to spin their polarizers throughout time and report where photons arrive successfully or unsuccessfully at their detectors. What does this mean? All of these phenomena are at the heart of the modern quantum computing revolution. The idea that quantum computers will outperform classical computers in the not-too-distant future because they have the inherent advantage of their particles communicating with one another at their core. Although it may be tempting to believe that people can currently communicate faster than light, the field firmly rejects this notion. This is because the core of this phenomenon is inherently unpredictable at the source of photon, or entangled particle creation, as well as at the measurement points. Each photon will or will not pass through a polarizer. Each photon will be formed in one of several states, which will eventually be difficult to determine. Until measured, there is no way of loading information onto that communication channel, and as a result, there is no way of violating Einstein's fundamental contribution, which is that the speed of light is a fundamental limit in the universe, which is correct and, I believe, will keep Einstein happy. One thing is evident as we come to an end with our discovery of the captivating and thrilling world of quantum physics: it is far more perplexing and fascinating than we could have ever anticipated. Our understanding of reality is changing, which forces us to reconsider the fundamental principles guiding our existence. What do you think about the possibility that the universe may not exist as we know it? Leave your thoughts in the comments section below, and together, let's carry on this stimulating discussion.